Okay, so we're going to be able to easily now do curl of f dot our normal vector. And we're going to do that in a minute. But while we're here, we're also going to talk about the integral of this del dot f, this divergence integral on the volume. And I'm not going to say too much about that because it's very straightforward. We know, according to this set of inequalities, on the x squared plus y squared plus z squared equals 1, corresponding to the x squared plus y squared plus z squared equals 1 formulation or description of the unit sphere, that's going to correspond then to an integral from -1 to 1 with respect to x. Can't read my handwriting here, it's not very good. Okay, this integral with respect to x, and then y from square root of negative square root of 1 minus x squared to the square root of 1 minus x squared with respect to y, and then z from this negative square root to the positive square root here. And then I've got this little circle here, which I'll kind of... Okay, that little circle there contains whatever it is you're trying to integrate. Okay, well, what is it we're trying to integrate? We're trying to integrate the divergence del dot f, the divergence, that's what we have here. So that's what we're going to put into this little box here. So we're going to have what turns out to be a pretty straightforward integral. Now we'll have to do a little integration by parts. So it's not trivial, there's going to be a little work involved, but nothing that you don't know from first year calculus, assuming that you worked hard enough to learn how to do basic integration and integration by parts and substitution and so forth. And if you didn't, you probably need to refer back and keep doing these integrals until you get good at it. I know that takes time. Okay. Then we're going to have a surface integral to do. Okay. The surface integral I've got a dA here, and I didn't, I was going to include, okay, if I use a dA here, okay, if we're doing a surface integral for the unit sphere, if we're doing 1/2, upper half or lower half of the unit sphere, we can do that by a single integral. Left a negative sign off here. We're doing that by a single integral over the circle on which the unit sphere meets the xy plane. Well, we know what that is, and we know that the parameterization of that unit circle is the same as the parameterization, I'm sorry, not the parameterization, but the inequalities that describe that unit circle are just these, the inequalities we used when we parameterized the upper hemisphere. So we're going to have an integral like this with respect to a, okay, and dA is going to be our dx dy. What is it that we're integrating? We're integrating here the curl of f dot our normal vector. Okay, curl f dot n. Now we use the capital N, not the little n. Capital N we got here because it includes already our area increment, our area multiplier. Okay, we don't use just the unit normal in this case. We could use the unit normal, then we'd have to figure out the area multiplier, which would be easy to do. We could use this, okay, or we could use just dot f with this vector. But that's going to be easy to write down, and the integral might or might not be straightforward. I think we're going to do that in the next video clip. So we can say that the curl of f dot ds, integral of curl of f dot ds, is f dot ds, where the ds is a vector, equal to n dy dx, or to the curl of f dot our little unit vector times, and I have dA there, and that's just wrong. Times ds, where ds is not a vector, it doesn't include our normal vector, okay? And just to be clear, ds without the vector, pick a different color. That doesn't contrast very well, but there it is. It's just the area multiplier times our area increment. The ds vector could be written as normal vector times your dA, where dA is the dx dy area down in the plane, divided by n dot k, as we talked about when we first started working on surface integrals. So there are many ways to conceptualize this. You're going to see it written out at least 2 or 3 different ways in your text. And if you're looking at different texts, you might see just about anything. So I'm going to cover every possibility, but it's much to your benefit to understand how all these increments work together. Now we're going to boil it down to one way of representing the area increment in the curl of f dot ds integral. But we'll do that in the next video. And I did it here again. Kind of unfortunate. I'll correct it right now. This would be our ds without the vector. Okay? And then if we use this, for our scalar ds, we've got to use the unit normal here. If we use the ds here, this one, the big N normal, includes our area multiplier, which is this or this. Well, it's magnitude of n over magnitude of n dot k. Okay, well, I don't want to go too far into that. We'll see how this works out. We'll actually do the integral. We're not going to actually do this integral. Okay, this integral is straightforward, just another volume integral. We're integrating this function, and we just use straightforward integration techniques. Surface integrals are a little more complicated, so we want to do another one.